So in APM 105, we spend about 2 weeks or so reviewing basic algebra skills that are really foundational to mathematics and also will be really important in your success in this class. A lot of calculus, unfortunately or fortunately, depending on your background, is based on algebra. And so we're just going to spend a little bit of time reviewing some basic algebra properties like exponents, orders of operations, factoring, and some other things before we dive into actual calculus. This stuff may be review for you. If so, that's great. If I know that everyone has seen this before, but please take the time to really make sure that you are strengthening whatever foundation that you have come into the class with. So we're going to work with the first 4 sections of, this is an appendix in the back of our book. We're going to call it Chapter A, and it's a bit of a pre-calculus / algebra review, like I said. So the first section, A.1, is just a review about how numbers work, what a real number is, and the real number line. And in addition to that, we're going to review interval notation, as well as solving inequalities, and then look at one application that we will have that will appear in this class over and over that may be new for you. So let's get started. The real number line in order. So first, what is a real number? Well, real numbers are essentially every number that you can think of. So we have things that are called natural numbers, we have things that are called integers, we have things that are called rational numbers, we have irrational numbers, we also have imaginary numbers. Those numbers are the only ones that are not included in what we call real numbers. Okay, so this is just conceptual stuff. You don't have to, I'm not going to really test you on this or anything like that, but just to give us some background. So real numbers are made up of irrational and rational numbers. Oops. So in other words, they are not imaginary. So no dealing with I, which is the square root of -1. That is not a part of this course at all. So if you didn't like that in your Algebra 2 class in high school, no worries. That is not something that we're going to address at all this semester. Here's just a little way that we can kind of conceptualize or visualize what the real number set looks like. So if we pretend that this box here is all of the real numbers, we do have a symbol. We have some varying symbols for different sets of numbers. In R, with like kind of a double line on the side, stands for the real numbers. Okay, so every single real number can either be irrational or rational. So we're gonna kind of divide this up. It's not quite half and half. It's actually very not much half and half at all. There are way more irrational numbers than rational numbers. But for the sake of just having space to write these things in, we kind of have to make it look this way. So we can call, let's say the left-hand side here is rational numbers. So we represent that with a Q for quotient, because rational numbers can be written as a fraction. And we can represent the irrational numbers with this symbol. It's kind of like, I don't know, an I with a double bar in the middle. Okay, so these are irrational. And these are rational. Some examples of irrational numbers are things like pi, which is about 3.14159, etc. It goes on and on forever. And then also we have the number e, which is an irrational number. That's about 2.7818. Again, goes on forever, does not terminate. It is an infinite decimal. And then also a common, just one more example of an irrational number is the square root of 2. So irrational numbers arise from numbers that are square roots of things. So square root of 2 is about 1.414, etc. Of course, there are tons and tons more. These are just some examples. In the rational side, we have things that are fractions, things that can be represented as fractions. That's what rational basically means. And so, some examples of some fractions, we've got, I don't know, how about -3/2? We've got, how about 1/2? We've got, I don't know, 4/5. Tons more, right, that fractions you can come up with. And then we can also refine our kind of sense of thinking about rational numbers even further, because there are some numbers that don't quite look like fractions. So we've got things like the integers, which are a subset of the rational numbers. And the way that we represent the integers is with a z, and again, double bar in the middle. So the integers are things like whole numbers, positive and negative. So these are numbers, for example, like -1, 0 is an integer, +5, any positive or negative whole number, including 0. Then, even smaller than that, we're kind of going backwards. The way that these numbers were discovered was actually, this last set here was discovered first, or thought of first. So inside of the integers, we can also think of just the positive integers, right? So like the numbers you use to count things, like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and on and on and on. And those are called the natural numbers. So that's like an n with a double bar on the side. And these are numbers like, actually 0 isn't quite included in the natural numbers. It's like 1, 2, 3, etc. All the counting numbers. So this, again, isn't all that important, but this is just, as you're working with numbers every day in this class, we will not encounter any number that is not in one of these kinds of classifications. So whenever I see a number, I kind of have this, sense of like what kind of number it is. And so it's good to think about that. So we use something called the real number line that gives us a better picture of the real numbers, because that picture that we just drew is not really workable. You don't use that to really represent stuff. It's just a way to kind of conceptualize. So the real number line is actually a better way to represent all of the real numbers. And normally how we draw it is just like this. It's a line with 2 arrows on either side because it goes on forever in both directions. And it's a solid line, but really what it is made up of a lot of different points, like infinitely many points, if you can kind of think of that. So the reason why the real number line is great is because each point on it corresponds to one real number. And every point on the real number line, and vice versa. So each real number line can be thought of as a point on the real number line. I think I messed that up, but I think you know what I mean. So we have to kind of tell everyone where we are, looking on the number line. And so normally people center it at 0 because that's a nice place to, to organize things. And so normally, everyone writes things in a certain order. So to the right of 0, we go this way, we've got positive numbers. And to the left of 0, if we go out this way, we've got negative numbers. So all numbers, all real numbers exist on here. So we can put little dashes wherever we'd like. So if I'm going to say that that's 1, then, the same distance out, we'd say that that's 2. We'd say, maybe 3 is here. And we can also look at every single point in between as a number. So, halfway between 0 and 1 might be like 1/2. Here's a rational number that is on the number line. E, our irrational number, is 2.7-ish, so that's about like here. And so here's where E lives on the number line. Negative numbers go the opposite direction, so -1 might be right here. We've got -2, -3, etc. It goes on and on forever. And so we can plot some negative numbers here too. Right here is about -1/2. So that might be -3/2. -pi would be about here. And so anyway, this is just a reminder of how the real number line works. Some important properties of the real number line. Important properties of the real number line are, 1, that it is ordered. Like we just saw, it has a sense of direction and an order. The numbers aren't randomly placed. They go from increasing to decreasing. From smallest to largest is what I mean. That's a better way to say that. Another important property of the real number line is that it helps us to represent solutions to things called inequalities. So it's a nice picture. Okay, so we're going to take some time right now to really focus on this aspect and remember or review how to use the real number line to find solutions to inequalities or represent them. And then we'll practice actually finding some solutions. And so this is called interval notation. When you are focused on representing a large set of numbers, like from -3 up until 2, like all of those numbers, that's called an interval. It has a starting point and an ending point. We have several different kinds of intervals, the first of which is called an open interval. So the open interval does not include the endpoints. Okay, so for example, I'm just going to draw, we're not going to use numbers, we're just going to use general placeholders here. So let's call this like A, how about, and let's call this B. And so we would call the open interval between A and B, how we would represent that on the graph, it's going to look like, okay, well, it's going to be all the numbers between A and B, so we're just going to shade it in. And then the open part means we're not including A. So to denote that, we kind of draw an open circle like this. And we're not including B either, so we draw an open circle like that. So this is all numbers between A and B. And so we would could call this the graphical way. This is a graphical way of representing that. This might be, a way to represent that in words. We want to also be fluent in, translating from several different ways of thinking about intervals and such. So we can also represent the same relationship in an inequality. So all numbers between A and B, but not including A and not including B, what that would look like is, so we use X to represent like any number that we want, but we don't know what it is. So X is between A and between B. So we have A is less than X, which is less than B. X is between A and B, and we're not including A or B, so we don't put the like equal sign here. It's just strictly less than in both cases. Okay, so these mean the same thing, this graph, this inequality, this phrase here. And switching to the last most kind of preferable type of way to write this would be interval notation. Okay, so this is the way that we want to be able to shift to. And the way that this gets converted into an interval, or the way this graph gets converted into an interval, is it's kind of weird because it looks like a coordinate point, but it's not. So we put the starting point, comma, the ending point, and then if we are not including the endpoints in the interval, we put parentheses. That's not a great parenthesis. Let's say like that. Okay, so this is the interval from A to B, not including A, not including B, and it means all the numbers between A and B. So this, again, means that as well. All right, we're going to be using intervals a lot, so that's why we're focusing on this at the moment. So the next type of interval is a closed interval. So this is exactly the same, except it includes the endpoints. Okay, so it includes both endpoints. So let's just use A and B again. We're going to still want to talk about, okay, all numbers between A and B, but this time I want to make sure that A and B are included. So instead of an open circle, we just kind of put a closed circle there. All right, the inequality that this would be represented as would be, okay, all the numbers that are between A and B. But now when I want to include A and include B, we put less than or equal to. Okay, the interval between A and B, starting and ending points are the same. However, now I want to indicate that we are actually including those points. So instead of the parentheses, we put, I don't know if this is a brace or a bracket, and that indicates that we are including A and B. All right. We can have some form of like mixture here. So we call these neither open nor closed intervals. So kind of half and half. So if you have a mixture where you're including one endpoint but not the other. So let's just do the same thing when we've got A and B. All right, let's say that we're talking about all the numbers between A and B, but here we want to include B in our interval, but we don't want to include A. All right, so in an inequality, excuse me, what this graph would be represented as in an inequality is going to look like A is less than X is less than or equal to B. And in terms of an interval notation, we just have a mixture of this open parenthesis and this closed brace here. Okay, so the starting and ending point is still A and B, but we're not including A and we're including B. And that's it. All right, next to this, I've just got another graph because we can have the including and not including in the opposite order. So if we've got A and we've got B, say we want to this time include A, but B is no good, so we're going to exclude that. So this would look like this in inequality notation. All right, and then in interval notation, which again is what we want to aim for, but the pictures can help us, is going to look like this. Starting and ending points are the same, but here this indicates we are including this endpoint, and here we are not. That was a little abstract because we don't have numbers here. We're going to get to some examples with that in just a moment, but this is really all of the types of intervals that you can encounter, aside from these last set down here, which we'll talk about right now. Okay, so the ones that we've seen so far here, they've got sort of, they're confined, like they have a starting and an ending point. Right there, we call them finite. You can have infinite intervals. So you can have ones that go on forever, that don't have a point that stops them in one or more directions. Okay, so let's say, for example, you want to talk about all the numbers let's say here's B, all the numbers that are greater than a certain number. So all the numbers that are larger than B. So we kind of just shade this like this. And whether or not we want to include B will affect this. So let's say for first, let's not include B. So this is all numbers that are greater than whatever this number B is. So how we would represent that in inequality notation is going to look like, okay, all numbers X that are larger than B. Okay, this is where it kind of gets a little backwards. I think the pictures are really helpful with interval notation. With interval notation, we always want the lower number first and the higher number second. In this case, the lower number is B, and we're not including it. And the higher number, well, there really isn't one, right? So we use infinity symbol. It's really fun to draw. And we never include infinity in our interval because it's not an actual number. It's just a symbol that represents the concept of getting larger and larger. So here we have an open parenthesis there. All right, right next to that, we can do the same thing, but we can put a, including B. So we could want to talk about all numbers greater than or greater than B or equal to B. So this would look like X is greater than or equal to B, and B will just be a number. And the only difference here in our interval notation is that this is going to now include B. So we're going to have a closed brace there. So B to infinity. All right, a few more here. We can have sort of the opposite direction. So if we want to talk about all numbers that are less than a certain number, say A, that would look like this. We shaded our number line here. And whether or not we want to include A is going to make a difference. So let's first see what that would look like if we do not include A. So we have an open circle. Okay, so this would be all numbers that are less than A. So X is less than A. And all right, we've got to think about what our starting point and our ending point are here. So because there's no beginning, this would be negative infinity, way out in that direction, just getting more and more negative. So that's going to be kind of our left point for our interval notation. Again, we have an open interval because, a parentheses here because we're not including negative infinity. And then we're going up to A and not including A. All right, then we can have the same deal, but here we can include A. So it's just going to look like that with our closed in circle. This would be all numbers that are less than or equal to A. And so that's going to look the same in interval notation again, except at A, we're closing that part of it. So we're using that brace or that bracket instead of the parenthesis. All right, the very last type of interval is infinite in both directions. So this is literally the entire number line, all real numbers. Just shade that whole thing in. That's what the graph of that would look like. So this is all real numbers. Okay, and the way to represent that is, well, the lower point, negative infinity, the higher point, positive infinity. We never include either of those, so we've got parentheses on both sides of our interval here. And so negative infinity to infinity means every single number with no restrictions, except that it's real. All right, so let's practice kind of solving some inequalities and putting our answer in interval notation. All right, so the first example that we're going to look at is 3 minus 2x is greater than 1. I assume that you've solved inequalities before, so I'm going to just kind of go through these as a reminder, a refresher of some skills. Really, solving these is exactly like solving, what you would do if this were equals. with one special thing that I'll remind you of with switching the order. And by order, I mean like the direction of this. So we'll get there when we get there. So the first one, 3 minus 2x is greater than 1. So, you know, the idea here is to isolate the x on one side of the inequality symbol. So order of operations to do, the first thing to do first would be to isolate this chunk. So we've got this 3 here that we need to get rid of first. So the opposite of having a plus 3 is having a minus 3. So we're going to subtract 3 from both sides. From both sides, the side that I'm talking about is, you know, through the inequality symbol. Okay, so we've got the 3 minus 3, those cancel out or they add up to 0. All right, we've got negative 2x left over on the left. 1 minus 3 is, what is that, negative 2? So there's a simpler inequality. Now we want to get the x alone on one side of the inequality. It is being multiplied by negative 2. And so to undo that, we are going to divide by negative 2. Okay, now this is going to divide to give you a 1x on the left side. On the right side, we've got negative 2 divided by negative 2. That's also 1. However, here's the thing that we've got to remember when working with inequalities is that when you divide or multiply by a negative number, remember you must switch the direction of the inequality. So if it's going, you know, if it's less than, then it becomes greater than. If it's greater than, then it becomes less than. So in this case, this is going to become less than. So that's what's happening right here. And that's, once we're here, once we have x on one side by itself, then we've solved it. So, you know, all numbers that are less than 1 is our solution. So any number that's less than 1 that you plug into here is going to make this original thing true. And that's what we just discovered. So in interval notation, right, that's what we're looking to do here, put your answer in interval notation. If you are not sure how to do this from just the inequality, you can flip back to your notes and get used to it that we just talked about. Or I like to draw a little sketch that helps me. So I know that 1 is an important like kind of place where things happen. And I want to talk about all numbers that are less than 1. So it's going to look like this. Right, and I'm not including 1, so it's going to have an open circle. And that's kind of easier for me to write an interval. So this is going to look like, let's see, negative infinity, right, up until 1, and we're not including 1. And so there's our answer in interval notation. All right, number 2 is x plus 1 is less than negative x divided by 3. Now, most of the time in our classes, we won't have time to do a ton of examples, but I choose the examples that we're doing most of the time to illustrate a certain thing. So in this previous example, right, this was something that I wanted to remind you of. In this example, something that I want to remind you of is how you can avoid working with fractions, right? I know that some of you, when you saw this fraction here, you may have started feeling bad or like anxious, or, you know, it's something that most people don't want to deal with. I love fractions, but I understand that it's not for everyone. So I'm going to remind you of a way that you can actually eliminate them. All right, so it's called clearing fractions. So here we've got this divided by 3 here. This is just an option. It's not what you have to do all the time, but I would recommend to always do this. So let's see, to clear the fraction, all you need to do is multiply everything on both sides of whatever it is by the denominator. Okay, so here it's a 3. So we're going to multiply both sides This works for equalities like equations as well. In this case, we're going to multiply both sides by 3. All right, so let's see. So parentheses here, this whole thing is being multiplied by 3. This whole thing is being multiplied by 3. I think why we want to do this is because now 3 times negative x divided by 3, those divide to give you 1. It's like we did nothing, so those can go away. Okay, on the left-hand side, we've got 3 parentheses x plus 1. The direction stays the same because this 3 was a positive number. And then on the right-hand side, we have negative x. Now this should be much easier to solve. Except here we've got an x here and an x here. So we've got to kind of, pull this x out of its tracked parentheses here. And the way to do that is to distribute the 3 into the x and the 1. So this will become 3x plus 3. Again, we want to get the x's alone on one side of the equation. So inequalities, we want to combine the x terms. Either way you want to do it is fine. I'm going to bring the 3x over to this side. So that will be done by subtracting. Okay, so 3x minus 3x adds up to 0. Negative x minus 3x, we have negative 1 and we're taking away 3 more, so that's minus 4x. And then lastly, we want to get the x alone, so like 1x on the right-hand side. So we're going to divide by negative 4. Okay, again, we're going to need to switch the inequality here. Now 3 over negative 4, that's the same as just negative 3/4. We're going to swap it to be greater than here, and then we've got x. Okay, so just here is what happened here as well. And that's our solution in inequality form. Now it might look weird because it's kind of the opposite order. So you can always rewrite these, just read them backwards. X would be less than, kind of just reading it the other direction, negative 3/4. So we can also write it that way too. Then we want to put this in interval notation. Now, as we're going, I encourage you to kind of like pause these at certain times and try things on your own, because I think that's a really good way to be actively participating in kind of watching the video. But anyway, so it's good practice to do that whenever you can. So here's our, just a stepping stone, draw a picture here. So we've got negative 3/4. We want all numbers that are less than it. Okay, so it's kind of going to look like the previous example. Right, all these numbers that are less than negative 3/4, but not including it. And so the way that that would be represented would be negative infinity, open parenthesis, up to negative 3/4. That's also an open parenthesis. So again, what we found is that if we want to plug in an x value here and here in our original inequality, that would make this whole thing be true. Sometimes this thing lags a little bit behind, which it is doing right now. Then any number that is between negative infinity and negative 3/4 would do that. So any number less than negative 3/4 would be a solution. All right. We've got 2 more of these, and then we are going to move on to an application. This is calculus and its application, so we have to include those in here, which they are more interesting in some cases than just pure math. All right, so here we've got this kind of, I don't know, a string of inequalities. Okay, we've got 3 pieces, a left piece, a middle piece, and a right piece. It's no problem at all. You can still, use the same things that we're used to, except this time we're going to want to isolate the x term in the center or in the middle, because we want to be able to sandwich the x between some numbers. There are several ways that you can always go about any math problem. The way that I am going to go about this is one way. All right, so the first thing that I would recommend that you do to get closer to just isolating this part is to get rid of this +2. Okay, so I'm going to do subtract 2 from all three quote-unquote sides here. Right, and if it helps you, you can definitely like kind of draw these dashes here. So let's see what we've got. We've got 1 minus 2, so that's -1. Okay, we are subtracting 2, but we're not dividing by -2, so the directions are going to stay the same for the inequalities. In the center, we've got 2 minus x divided by 2. And on the right side, we've got +6. We're getting closer to having x in the middle. The next thing that I would suggest, again, there are many ways you can go about this, but if you remember in our previous example, when I was showing you how to get rid of a fraction, what we should do here to get rid of that is to clear this fraction by multiplying everything by 2. Okay, so we're going to multiply all three sides, or all three, I don't know if you call it, I don't know, every part of this inequality by 2. So let's see what's going to happen with this. So we're going to do 2 on the left side, 2 on the middle, 2 on the right side. Okay, now on the left side, we've got 2 times -1, so that's -2. The directions of the inequality stay the same because 2 is a positive number. Then we've got 2 multiplied and then divided by 2. So that's essentially like you did nothing, right? They divide to give you 1. And so in the center, what we have here is 2 minus x. And then on the right side, what we've got here is 6 times 2, which is 12. All right, this looks better. We are closer to isolating the x in the center. The next thing that we should do to get the negative x alone here is to get rid of this 2. It's basically added here, so we're going to undo that by subtracting. All right, -2 minus 2, be careful there, that's not 0, it is more negative, so it's -4. The negative is attached to the x here, so we've got -x in the center. We've got 12 minus 2, and that is 10. And the very last thing is to get rid of that negative sign in this center. So to do that, we're just going to divide everything by -1. Right, that'll give us a positive x in the middle. Now here we did divide by a negative number. So we have to switch directions of both inequalities. Okay, so let's see, this is going to become a greater than. This will become a greater than or equal to. And -4 divided by -1 is +4. 10 divided by -1 is -10. And there we go. It looks a little bit weird because we normally, write it kind of reversed, right, with the lower number first. So you can totally just always read inequalities backwards. So we'll say -10. This will just change its direction. Then x. Then this will change its direction, and then 4. So we could say -10 is less than or equal to x is less than 4. All right, so this is all numbers between -10 and 4. So if you want to make a number line here, right, to help us on the way to interval notation, what that's going to look like is all of these numbers between these guys. We're going to include 10, so closed circle. We're going to not include 4, so open circle. And remember, this is just a stepping stone to get us to interval notation, which will look like -10 to 4, closed bracket at -10, open parenthesis at 4. And so there we go. There is our solution set to this inequality. Any number between -10 and 4 that you plug into here for x will give you a true statement. All right, our last type of inequality that we're going to look at today before our application is one that has a degree of 2 or is a quadratic. We are going to review factoring, but we're going to need it just briefly in this example. So I expect that you have factored things before. So here we go. It is x squared plus 2x is greater than or equal to 8. Okay, so like I said, we've got a quadratic here. This means you've got to do something kind of different, right? So normally in the previous 3 examples, we isolated the x on one side of the inequality. But you notice here there's an x squared and there's an x. You can't just isolate the x because there's always going to be more than one. And so the procedure is, like I said, is different. All right, so the first thing we want to do is to get 0 on one side of the inequality. You might remember when you are solving quadratic equations that you need 0 on one side, and we'll review that as well. But that's kind of the same reason as why we're doing that here. All right, so the way to go about that would be minus 8 on both sides. Okay, that's going to give us x squared plus 2x minus 8 is greater than or equal to 0. All right. So now you may remember, I hope that when you have a quadratic, so anything with squared, so quadratic equation or a quadratic function, when it can be 0 at some places, it can be positive at other places, it can be negative at other places. You might remember that these are parabolas that open down or open up like this when you graph them. We'll also review graphing. And so what we want to do, it's got some places where, for example, this one is going to open up like this. When you graph this, it's going to have some places where it's positive above the x-axis, greater than 0. Some places where it's negative below the x-axis. And then there's these places where it crosses the x-axis, where it is equal to 0. So if we can find where this equation here is actually equal to 0, those places where it could switch from positive to negative or vice versa, then what we can do is test numbers on either side of those places and kind of get a sense of the sign of what's going on those intervals. All right, so that might have been a lot. Let's just go through and see how this goes. So we want to first, I'm going to write the steps over here. So let's factor. Okay, so in a brief review how you factor something like this. We have these 2 sets of parentheses. They get factored into linear pieces, x to the first. And we need 2 numbers that multiply to this number here, the negative 8, but add up to positive 2, the middle number. Now those numbers are going to be what we've got, positive 4 and negative 2. I think those numbers multiply to negative 8 and add up to positive 2. Okay, so what this means, once we factor, this helps us find the zeros. Okay, so x plus 4 times x minus 2 is equal to 0, right? When you plug in x equals negative 4, because that will make this whole part 0. No matter what this is, it doesn't matter. 0 times, I guess that'll be negative 6, right? It equals 0. Okay, or x equals positive 2. Right, when you plug in a 2 here, we're going to get 6. We're going to get a 0. So 6 times 0, that equals 0. So those are what we call the roots of this quadratic right here. But everywhere else, the sign of this this part here is going to be either positive, which is what we're looking for, greater than 0, or negative, which is not what we're looking for. That would be less than 0. Okay, so all I've got to do is test some points. Okay, so we're going to test some values. Okay, so let's make a number line. So let's do, so we've got -4, we've got +2. We know that these are where the thing that we're looking at is equal to 0. So in this interval, and in this interval, and in this interval, the sign of this thing is going to be either positive or negative. So pick any number. Let's test, how about x equals -5 in this interval. So a number less than -4. You could pick -6, -7, whatever you like. Okay, and what we're going to do is we're going to plug in a -5 into either here or here and see if it makes this inequality true. So in other words, if it's positive. So let's plug into, so we've got x plus 4 times x minus 2. We want this to be greater than or equal to 0. So let's plug in -5. I'm going to put a question mark here, like, is this true? Okay, -5 plus 4, all right, that's -1. -5 minus 2, that's -7. Is that greater than or equal to 0? That's +7 on the left side, so yes. Okay, so this is good. This is a good interval. This makes our inequality true. So we're going to shade this. This is part of our solution set. And one question is, are we including -4? Well, when you plug in -4, we have equal to 0. And our original inequality was including equals. So yes, we are going to include -4. All right, let's test a value between -4 and +2. So I don't know, 0 is a nice number to plug in. Okay, so we're going to plug in 0. We're going to ask ourselves, is that greater than or equal to 0? Well, this is 4. Then we've got times -2. That's -8, so that's not going to be a solution. So we're not going to shade that center interval. Okay, then we've got one more. This is numbers greater than 2. So let's try x equals 3. That's a number greater than 2 that lives in this interval here. So we're going to plug in 3. So we'll do 3 plus 4 times 3 minus 2. Is that positive or greater than or equal to 0? Let's see, 3 plus 4 is 7. 3 minus 2 is 1. That is true, right? 7 times 1 is 7. That is greater than 0. So we've got all of this as a solution set as well. And when we plug in 2, that gave us equals to 0. So that's going to be included in our solution set. This is a funky looking interval. We do want to put, it's kind of 2 intervals put together. Okay, so let's see. So we've got our first interval here. All right, so this is going to look like -infinity up to -4 and including -4. All right, that's that interval. Then we've got this interval here, which is 2 and greater. So it's going to look like close interval 2. No stopping point at the end, so that's to infinity. And then we can say and, or we can put a union symbol, right? This means union, we're combining 2 of these intervals together. Actually, we do want to use that, so let's prioritize that union here. So this just means union and, so combining together. All right, and there we go. There's our solution to this inequality.